So welcome to week 5 of the Applied Logistic Regression course, and today we're going to talk about statistical adjustment, and we're going to talk about the issues of interaction and confounding. Now, in multivariable logistic regression, each estimated coefficient provides an estimate of the log odds ratio, adjusting for all of the other variables included in the model simultaneously. And we talked about that, and so I hope you understand that. But what do we mean when we say adjusting statistically for other variables in the model? And to answer that question, we first have to consider the linear regression model known as the analysis of covariance. So let's suppose that we have a continuous dependent variable y, say y is weight, and we're interested in exploring whether two groups of individuals are comparable with respect to their weight. So let's let x equal 0 if the individual belongs to group I, and 1 if the individual belongs to group J. Now, unfortunately, it's not enough to simply compare the mean weight of people in group I to the mean weight of people in group J, and that's because there could be another variable, say age, that's related to the dependent variable. And so if the two groups differ with respect to this third variable, they would also differ with respect to weight. Therefore, our goal here is to adjust for age, that is, make the groups equivalent with respect to age before we compare the groups with respect to their weight. Let me give another, perhaps silly example. Suppose that I wanted to do a study that concerned blood pressure. And I have no idea who has higher blood pressure, males or females. And so it's my hope that I can get a sample of males and a sample of females and take the males' blood pressures and the females' blood pressures, and then I can compute the average of both groups and I can see which group has higher blood pressure. So this is the day I'm going to get my group of one of the groups, and I'm walking outside, and just at that moment the women on the track team at my university ran by. So I thought, oh, there's a group of women. So I go to the coach and I say to the coach, do you think I could get the blood pressures of the women on your team? And he said, it's okay with me if you go to them, and if they're willing to have their blood pressure taken, it's okay. So I go there and I ask the women if they were interested in having their blood pressure, and they all did. So I got a sample of 20 blood pressures for women. Okay, so now I have my women's sample. Now, so I'm walking outside, I'm trying to think, where am I going to get a sample of men? And at that moment, I walked by a nursing home, and I thought to myself, oh, there are probably men in there. So I go in and I talk to the administrator, and he says, yes, we have men who are in here, so do you think they'd mind if I take their blood pressure? He said, well, you know, they're really old, and you know, maybe they won't know what you're asking, but you could try. So I went in and I talked to these men, you know, half of them were unconscious and, you know, and trying to get information and whether they're willing, and most of them were willing, so we took their blood pressures, and I have 20 blood pressures from men. So I have 20 women blood pressures and 20 men blood pressures, and I do my statistics, and I find out that the women have lower blood pressure than men. So I write up my results, you know, I say, okay, women have lower blood pressures than men, and I send it into a journal, and they reject my paper. So what did I do wrong? I mean, why would they reject my paper? What's the problem here? I have 20 women, I have 20 men, and as you can imagine, the reason is that there are other factors that are related to the outcome variable that are very different in the groups. For example, age. I mean, we know that the women were young and the men were old. Age is related to blood pressure, so the fact that I had young women and old men would tell me that I expect that the women will have lower blood pressures just because of that. And also, there's a question of fitness. I mean, the women are fit and the men are not fit, and fitness is related to blood pressure, so that's different as well. And so there are many issues here about why this is not really a good way to do your study. Now, in not so much of an extreme case, what we have is we have that we may find that group 1 is much younger than group 2, and as a result, group 1 might be much lighter than group 2. But if we were able to control for age, there might be no difference whatsoever. So analysis of covariance is a way to control for some unwanted variable in the analysis stage of the study. sometimes if you know about something ahead of time, you can control for it through the way you sample. You can match. You can do many things that you can get rid of a variable if you know about it in advance. But typically in epidemiology, we have studies of populations, and we take the males and females the way they are, and there may be inherent differences between the males and females. And so we have to have some way to control for this unwanted source of variation in the analysis stage of the study, not in the design stage of the study. So consider this figure, and so imagine that group J are men and group I are women. And if these lines are parallel, then I could tell you that that men have higher blood pressure or higher weight, whatever we're studying, than women, irrespective of which age I study. So and the true difference between men and women is this difference here, W4 minus W3. Because that same difference would hold if I was studying it at this age or at this age. Any age that I study, I would have the same difference, W4 minus W3. But the way the sampling was done, I might have very young women, and if I have young women, we might see that their average age was W1. And I have very old men, and we can see that their average weight was W2. So when I look at what I have in my sample, I have the difference between W2 and W1, which is much bigger than the true difference, which is W4 minus W3. So this is the problem. The problem is that the groups are not similar with respect to age. Age is associated with the outcome, and as a result, we have a biased idea of what the true difference is between the groups. So we have to try to control for this variable that differs between the groups. So for this analysis, what we have to do is we have to assume that the relationship between weight and age is linear, and we have to assume that each group has the same non-zero slope. So I have to assume that my lines are parallel. Now if we were doing the analysis of covariance, you could test both of those assumptions before you then make any inference about the differences. Now in this model, beta 1 is the true difference between the groups, because if you look at this, here's the males, they have slope beta 2, so do the females have slope beta 2, but males have an intercept of beta naught plus beta 1. Females have an intercept of beta naught. So the true difference between males and females is beta 1. So beta 1 is the true difference. They have the same slope, and because they have the same slope, I can focus on the intercept, and so males are heavier by the amount beta 2. So beta 1 is the true difference between the two groups, and beta 2 is the rate of change in weight per year of age in each group. It's the slope. The slope is the same for males and females. Males had an intercept that was beta 1 units bigger than the intercept for females. So it looks like, so that's the true difference between the groups. But let's suppose that the males, or the females in our case, had mean age of A bar 1. And the males had a mean age of A bar 2, as we saw here. Here's the males had an age which was much bigger than females. And so if that's the case, then the mean weight for the females would be W1. And the mean weight for the males would be W2, right? We saw that. For the females, it's W1. For the males, it's W2. And the difference between W2 and W1 is much, much bigger than the true difference, which is beta 1. So our impression of the difference in weight between males and females is being drastically inflated by the inherent difference in age between the groups. So this difference, W2 minus W1, I can write it down. The difference is beta naught plus beta 1 plus beta 2 times the average age of the males minus beta naught plus beta 2 times the average age of the females. And when you take this difference, you find that it's beta 1 plus beta 2 times the difference A bar 2 minus A bar 1. Now, beta 1 is the true difference. That's what I wish I could estimate. The problem is that the average ages are not the same in the two groups. A bar 2 and A bar 1 are not the same. And so I have a biased estimate of the difference in weights, and the amount of the bias is this second term, beta 2 times A bar 2 minus A bar 1. So what I need to do is get rid of this term. I need to somehow eliminate beta 2 times A bar 2 minus A bar 1, and the way we can do that is simply give both groups the same age artificially. So instead of the male's age being A bar 2, we'll simply make it A bar. And instead of the female's age being A bar 1, we'll make it A bar. So back to the picture, instead of males having age A bar 2, let's make believe it was A bar. And instead of females having age A bar 1, let's make believe it was A bar. Now the difference is W4 minus W3, not W2 minus W1. And W4 minus W3 is beta naught plus beta 1 plus beta 2 times A bar, because I forced it to be A bar, minus beta naught plus beta 2 times A bar, and the difference is now beta 1. So that beta 1 is the true difference between the groups, and I was able to accomplish it by artificially giving both groups the same value of age, A bar. So let's have a break, and when we come back, we'll return to logistic regression.